And I think we're gonna go live for the Q&A. Hello, everybody. All right, testing the sound. We're going to go live for the Q&A. Can you guys hear me? Can you put a thumbs up if you can hear me? Yes, I see Johannes. And I'm waiting for others to come online. Okay, great. Well, thank you, everyone. Thank you to the audience for listening. Sorry for last week. We had unexpected technical difficulty, and you probably received an email right now that says that we will rebroadcast and redo the same session at the end of next week. So watch out for your email for that. We're extremely sorry for that, and we're learning from it, and it won't happen again. So for today's question, I have let's see. I have Johannes. I have, let's see. I'm trying to figure out if I can view everyone. There you go. I have Dinesh. I see Jacob. I see Dan. I see Niket. I see Artie. So thank you. Thank you, everyone, for speaking and for the presentation today. I'm currently located in the Seattle/Bellevue area, and as usual, it is raining today. So I'm going to start with a quick roundtable about, where are you guys? What's the weather? What's happening in your world? So I start with Dan.
Yeah, thanks so much. I'm Dan Schatzberg. I'm an engineer in the New York office, so work in kind of lower Manhattan. Weather in New York has been a little on the cold side, but with signs of things warming up and getting kind of nice, which is an exciting period of time for weather here.
Great. Then I'll move to Dinesh. Dinesh, we met in the past in person, and now we're virtual. So are you still in the same area?
Yeah, it's nice to see you virtually at least. I'm still in Cupertino, San Jose area. The weather is pretty nice out there today.
Great. Next one is Artie.
Hi, it's nice to meet all of you virtually. I am in the Bay Area in California, and it's bright and sunny.
As usual. All right, Johannes, upstate New York.
Yes, hello, I'm Johannes. Yeah, I live about 2 hours north of New York City in the Hudson Valley. And the weather, I would say, is about the same as for Dan.
Great. Niket?
Hello everyone. I'm in Menlo Park, Bay Area. The weather is great. Although like Saturday I was in Tahoe skiing and there was a snowstorm there. So that was quite exciting.
Awesome. Finally some snow there. And finally, Jacob.
Hi, I'm Jacob. I live in Seattle and I love this weather. So.
Great. It rains a lot here. Okay. So let's move to the user questions. So I'll try to bring a little bit of variety by alternating topics, and then we'll see what we got. So we've got a couple of user questions. So let's see. I'll start with question related to the first talk. So first question: with future technology like CXL, Compute Express Link, providing memory-like access semantics where pages are still mapped, how will TMO needs to be changed to understand how much memory can be
offloaded? Yeah, I can answer that. So TMO is currently built on top of PSI, which captures the overhead of paging, right? So obviously, if TMO demodes stuff from main memory to disk, PSI will measure the overhead of bringing that stuff back on demand, and that will cause the whole stack to back off if we are doing too much of that. Now, obviously, with CXL, the memory will be demoted to a second tier of memory, and it'll continue to be accessed in that second tier memory. There's no more paging back and forth, right? So we're losing our cost function there. We cannot currently tell the overhead of how much between the page being accessed from DRAM and it being accessed from second tier memory. We cannot tell the difference right now. So one area we have to improve there is we have to teach PSI to to capture that cost. Everything else already works. The reclaim process is the same. The promotion process is similar. It really just comes down to capturing the cost function of how much slower is that other memory? How much does it add to our general memory accesses like that? Yeah.
Great to know. I'll move to a question related to, for Dinesh, related to Cassandra. So let's see, which industry trends are shaping the database landscape, and particularly Cassandra? Like you mentioned some in the talk around, like, you know, people now are asking for reliability and durability, which probably was not in Cassandra's inception. So can you discuss that a little bit?
So Cassandra has been a durable and reliable database, but it focuses more on availability, and it has durability as a basic tenet, but it has what is called as tunable consistency. So the database can act both as a very strongly consistent database or absolutely inconsistent, right? Depending on how you write your application. As far as the question goes, right, around industry trends, I think the biggest industry trend is the scale and criticality of the data. So availability of systems has become even more critical now. I mean, COVID has kind of shown that everybody wants to work online from home, and that has really pushed our systems to the edge, where the data not only has grown in size, but also in criticality. So if your system is offline for a few minutes, the impact is even larger now that everybody's online. And other trends, including like IoT, wearables, and other devices, are pushing more and more data to the cloud. And then on the other side, we have machine learning, like we saw in some of the talks. We have machine learning and other use cases that are very hungry for data as well. So I think the core industry trend is the size of the data, criticality, security has become very crucial for all of us.
Great. Let's move to a question related to the talk from Jacob. So what would cause you to reconsider implementing geo-replication at the tectonic layer?
Yeah, so I should start by saying I'm not the best person to represent tectonic, but yeah, this was a topic that we discussed a lot as part of Manifold. So I think I'll try to talk about this.
Sure.
I expect it's always going to be a cost-benefit trade-off, and the two big costs are opportunity cost and complexity. And so, I mean, as these systems mature, we're picking off more and more of the low-hanging fruit. So the opportunity cost of doing something like this will probably go down. As for complexity, Tectonic is actually really modular. I drew it as this one giant monolithic thing, and that was really unfair. It's pretty modular, but it's not modular in this particular way. So adding this feature today would really kind of stretch the complexity budget. But I also think that will probably change as Tectonic continues to evolve and become more modular. But I think if you take opportunity cost and complexity off the table, and you ask, like, what would cause you to do this today without changing any of those things? I think what we've basically said is that complexity right now of this feature is kind of so inseparable from availability that at least all the workloads we have today aren't really worth that trade-off. So I think you'd have to find some scenario where we actually are willing to trade not just complexity but availability for whatever efficiency gains we could get. But I don't have any specific sense of what those would be right now.
Okay. All right. Let's move back to TMO. A question from the audience that happened during the talk. So, how much did the CPU increase with compressed memory usage? Because this is a trade-off that you're making. You're making a trade-off between, like, I'm going to use more CPU, I'm going to use less memory. So can you quantify a little bit the CPU increase that you observed?
Yeah, sure. I can take this. Yeah, so
Okay.
I think that's a question we get very often. In fact, when we were kind of piloting the Z-swap and TMO, that was kind of the first question that we would ask, because you're trading off more compute work for memory. So typically in our benchmarks in production, we saw less than 0.25% overall system level CPU usage addition when we do this. Although like we'll call out is when you do the page in, it's not like the thread can do something else, it's still waiting. And the overall throughput impact or the good put of the application was never impacted even for non-memory bound application. So we had this kind of discussion early on whether we should turn this on for memory bound services and not turn it on for non-memory bound services. But overall, what we found is like the CPU addition is kind of in the noise when you look at system level metrics and application level metrics as opposed to just the CPU level metrics. So yeah, it turned out to be the right trade-off.
Okay. I'll stay in the same area. So one of the trade-off is CPU usage. The second trade-off is kind of latency. So how did you measure the response time comparison between like swap and Z-swap?
Sure.
Yeah, I think I can take that. So there's sort of two ways of interpreting that question. One is response time in terms of like page fault response, or response time in terms of like our web server perceived response time. In terms of page fault, like PSI captures that latency and just tells us, exactly the duration. So with Z-swap, whatever the delay is, whether it's delay based on compression, delay based on in the sense of swap going out to disk, any of that, it's all captured already for us and rolled up into the like PSI metrics. In terms of the application perceived latency, typically for our workloads, like the way we measure performance is what is the peak throughput they can handle while keeping latency under some SLO. So something like say P99 latency should be under 100 milliseconds. So in any case where like this would increase the response latency, it would therefore decrease the peak throughput we could achieve. And our results sort of show that for our conservative configuration, the effect on latency wasn't enough to change peak throughput at all. As we start tweaking up even more aggressively, we did see some effect on peak throughput, and that is because of the latency impact.
Great. So I'll move to Haozhi right now about the data ingestion pipeline. So the first question is, have you considered hardware acceleration for data ingestion pipeline? From what I understand, the talk, there are some portions that you're moving, but can you elaborate a little bit more?
Yes, thank you for the question. It's a great question, in fact. So we basically deep dived on two components of the data ingestion pipeline, the storage tier and the data reading compute tier. For the storage tier, as we mentioned, we tend to be IO bound in our workloads. Currently production storage tier is HDD based. We also know from observing the data access pattern, there are hot features, which means about 40% of our stored bytes in any given partition can serve the reads of about 80% of the jobs reading that partition. Given all this information, hardware beefing up of storage tier in terms of SSD flash, which gives you more IO per watt, is a very interesting area, and our teams are actually working in this direction. On the data reading compute tier, which was the second tier, hardware acceleration there, there are basically data reading components that we execute decoding and decrypting data, and there is pre-processing. And hardware acceleration is being thought of moving the pre-processing component to like the GPU accelerators. In the future, it is possible, given how prominent this workload is in our data centers, of coming up with a hardware accelerator specifically for these workloads. And we are going to have a big optimization problem of where to do these pre-procs. Should you pre-materialize them? Should you do them in a hardware accelerator? Should you do them in a CPU, disaggregated CPU, or in the trainer itself? So it's a big optimization space in terms of hardware acceleration.
Great. Okay, with that, I'll move back to Dinesh about let's cover what are the feature that you're the most excited about Cassandra 4.0.
So the two features I think that I personally worked and contributed on are the faster streaming, which is the zero copy streaming. It really speeds up the performance of data replication within Cassandra, allowing it to be a more elastic database. And reducing risk as well. So your risk tolerance can be lowered. And the other feature I'm most excited about is the Z standard compression that allows you to save a trade-off, basically make the same trade-offs that we've been talking about in terms of burning more CPU for saving storage space, because Cassandra is a quorum-based system and it replicates its data. So 1 gigabyte of data is going to cost you 3 gigabytes in a RF3 configuration. And if you're doing multi-DC, it's going to cost you 6. So cost is an important part in any storage system. And with C standard, you get pretty much the same characteristics in terms of performance, better decompression performance, but compression is slower because of the CPU bound nature of that algorithm. And so I would say these are the two major things that I'm most excited about.
Okay. Talking about major thing, I'm going to follow up with another quick question around, like, you mentioned a 10x memory improvement. That's quite impressive. And I'm sure Dan and Johannes and Niket will kind of like be interested in figuring out how you guys did that.
Yeah, so I would say the 10 times improvement in memory efficiency comes from the fact that there are subsystems in Cassandra that haven't been refactored to use more modern paradigms. So one of the subsystems is the internode communication mechanism. And with Cassandra, we basically, every node is talking to every other node, since it is a completely distributed architecture where you don't really have a node performing a certain specific role. So so what happens is that each node needs to be able to talk to every other node. In existing pre 4.0 Cassandra, we used to maintain 3 connections to every node based on the priority levels of the messages that we are sending. And this was blocking IO based on threads. And so if you scale the cluster, you'll see each node is going to now require 3x the threads. So the thread count keeps increasing linearly with the size of the cluster. With async IO, we have bounded the number of threads that we use to about 10 or 20 or 30, depending on the size of the cluster, but it doesn't linearly increase with the size of the cluster itself. And so if you take an odd, like a 100 node cluster, you'll see that the number of threads you're spawning in Cassandra 3.0 are about roughly 300 for just internode messaging, not any other activities. Whereas in 4.0, it's about on the order of tens of threads. So that each thread costs you 256 kilobytes of stack space on the JVM's heap. And basically, if you see that memory efficiency, it reduces quite dramatically as you move to 4.0, because simply by the number of threads that you're spawning is an order of magnitude lower than what you would in a 100 node or 200 node cluster.
Great. Okay, from that, we all have a good, migration journey. So next question is for Jacob. So you guys have gone very far in the journey from working initially with, demanding key customers, onboarding them gradually, and then focusing on features and like integration work after the fact. Is there something like, looking back, like, we're in 2022 and you started on this work in 2017, maybe or earlier. Looking back, would you do something differently? Would you sequence this thing in another way?
Yeah, I think there are a couple things that obviously, you look back on a project this big, you'll find things you could have done better. As far as the rollout stuff, I think early on, we really cared about building a really general purpose system, and to sort of validate that strategy. We also really wanted to mix workloads that were different because that helps with utilization. So 2 customers that we rolled out within a couple months of each other were wildly different. One was the example I gave in the talk, which is this one that was migrating from Gluster and MySQL is really IO heavy workload. And another one was really small IOs and really small objects with pretty tight latency constraints. And we wanted to validate that we could run these workloads together. And like I said, we rolled them out fairly close together. And we proved that we could do it. We proved that we could actually get pretty good utilization, but there were a couple of glitches in the first year or so that they were both in production together. And these were things that they're just like low probability things. Like one case, we had a region go offline and then come back online a few hours later, and it caused this flood of traffic to one of the upstream services, which the system didn't really handle well. And I think that in retrospect, we could have put them both in production exactly when we did, like there was nothing wrong with that timeline, but we should have had better hardware isolation probably for those first 6 or 12 months while we discovered this last sort of long tail of issues. The other thing that comes to mind that we probably could have done better was we had the provisioning model that we had for Everstore was kind of limited in some ways. And so we wanted to introduce something a little more capable. And we got a lot of feedback early on that this was like not what customers wanted. And I think we thought it was an issue of us having to explain it better because it was new. And I think in reality, we should have just taken that feedback earlier and iterated on it more aggressively because I think the customers were right.
Great. All right, next question for our team. I'm gonna go with a very live question that just happened. So let's see how it goes. So every model access data differently. They need different stuff to be trained and so on. So how does your optimization work across model?
Okay, so that's a great question, and thanks for bringing it up. For example, the optimization we mentioned on feature flattening and feature projection. In general, we can say clearly in our production fleet that we do tend to read a subset of feature. This is dominant in most of our jobs in our production fleet. So as a net win, the selectivity of the wins we get from feature flattening due to high selectivity of our workloads as a whole gives us a net win in the efficiency of data ingestion. That said, if you have a model that is not selective, that is reading all the features, it is not going to have the same gains from feature flattening as we mentioned, but that is not the trend we see in production. Users tend to want flexibility in adding or removing new features, and we tend to see selective reads. So while there would be different percentages of selectivity, we can still say overall we have selective reads. So that's the optimization of feature flattening. We mentioned other optimizations in the associated blog posts like DPP, client-side rebatching, etc. And it really depends. Some models are heavily memory bound on their data reading computer. They see bigger wins from DPP client-side rebatching. Some models are heavily memory bandwidth bound on their data reading computer, and they see bigger wins from flat maps. We try to give a general array of optimizations that have worked.
Great. I'll move to Dan, Johannes, and Niket. So let's talk about upstreaming this stuff into the Linux community. So where do we stand? Is it available? Can you guys elaborate?
Yes. So all the components are upstreamed. We have PSI upstream. We've had it for a while, and we've used it also before TMO for internal debugging and stuff like that. So that's readily available, and most distributions enable it per default too. So if you have a standard Fedora, Arch Linux installation, something like that, it'll be there. The swap, our optimizations to the swap algorithm have also been upstreamed. So there's nothing you have to do there. They're just readily available when you boot a modern Linux kernel. There's one tiny piece that we use for where Senpai is interfacing with the kernel, where we initially built it against a existing interface in the C group control file system, and we switched to a private implementation of a slightly different interface. That's currently in the process of being upstreamed, but it's not a requirement necessarily. It just works a little better. It's a little bit more reliable, so it's not something that we necessarily rely on. Yeah, that's pretty much the status of that.
Great. I believe also you guys have published a paper about this. Could you tell us if it's available for the audience, where they can find it?
Yes, we submitted a paper that explains the entire TMO stack with a little bit more technical detail. That was accepted by ASP LOS, and that That just happened, so the paper should be available shortly.
Great, awesome. Now let's go back to Dinesh for a little bit. There's a quick question about like, what are the risks of reducing replication factor in Cassandra from 3 to 2?
I would say don't do it.
Yeah.
You can't achieve a quorum with two replication factor of 2. How do you get the majority of, right? In 2, there is no majority.
Okay. Next one about the latest GVM upgrade. So the latest GVM brings in virtual thread via Project Loom. Was that considered for Cassandra, like instead of moving to async IO?
Right. So Cassandra supported Java 8, and now we added Java 11 support. I don't believe Project Loom is in Java 11. So it is something that we will probably evaluate and how it performs in comparison to async IO would probably drive that decision.
All right. For Jacob, does Everstore use RuxDB? Because at Meta we tend to use RuxDB all over the map, even in MySQL.
Yes. So Everstore relies on RocksDB transitively through a handful of other systems.
Great. Let's see. I think we have the time for one more question. Let's see. Trying to find something that's super fast and super quick. Maybe for Dinesh, how does ZSTD compares to LZ4 with Cassandra? Like more CPU, what's the trade-off here?
Yeah, so Z standard versus LZ4 comparison is, I think, on the Z standard website. So for detailed information, you can look there. But just to be brief about it, I think it trades off more CPU for compression, but the decompression performance is same or better than LZ4.
Great. So we're at 11:45 on Pacific time, so we're at time. So I'm going to close the session. So thank you, everyone. Thank you for the participation. Thank you for the speaker. Thank you for the audience. Thank you for the what I call like meaningful question. And then we will resume this event next week at the same time. And have a good week.